Hello. Okay. Welcome to this short tutorial, which will teach you everything you need to know about writing code on the CAS. Um, so with this lesson, I'm assuming that you would have learnt the basics of pseudocode for a VCE standard. So you should know how all the basic blocks of pseudocode work. That includes if statements and loops and all that sort of basic stuff. And with this in mind, we can just jump straight into the code. So what I have here is just a blank document, and if you want to actually open the code, what we're going to do is, if you guys didn't know, you can open a new page by pressing Control plus I, and right down this bottom here, we're going to go number 9 for Program Editor. So let's click on that. Okay, we've got a new program. Let's just call it test. Okay, great name, test, like that, and boom, we have a program. So it's got some code here. What it's going to do is run through this code. So let's start. The first thing I'm going to talk about is how to define variables, because obviously writing code you want to have variables. There's several ways to do it, and the good thing is that it is quite similar to how you do it on a, just like when you're working away normally with your CAS. So one way you can do it is if I define maybe x equals to 1 like that. That is a way that I can define a variable. Another way I could do it is you can simply use the colon equals symbol up here, which many of you guys will probably already have been using, so maybe like that. The third way is that we can also use the STO button over here. So if I click on the STO button, it basically means store as. So like we're going to store 9 as a variable, maybe Z. Okay, so I've presented here 3 different ways of defining variables. Now, if you want to actually output something or print something, what we can do is, well, in the menu, the great thing about this CAS is that it gives you a lot of options for what you can actually do. Like if you look here, we've got like a lot of stuff we can do. In number 6, we have like this I/O menu, which actually stands for display. Sorry, not it stands for input output, and the first option on there is number 1 for display. So if we click that, it just gives us a keyword display. What we're going to do is simply display. So I can write disp x like that to display x. Let me now run this code to test it. So if you want to actually run it out, if you actually want to run this code, what we should do is go actions, no, not actions, number 2 for check syntax and store. And we want to first press number 1 for check syntax and store. This will basically verify that the code actually works, and then it's going to save it. Now, we can then go here to run. So it's going to open up a new page, and we're going to have our little testing here. Now, notice when we define our test, this is being defined as like just what you would consider a function. And because I've put nothing in this bracket, it looks a bit odd, but we're actually just going to run it like this, and it's going to run. And we see what we get is that x is equal to 1, which is what we expect. If you want to print multiple outputs, you could, go on this display, you could write this out again to go display Y and then display Z. Or what you could do instead is simply space your 3 outputs with a comma. So now, if I check the syntax, and then I can run it again, now it displays X, Y, and Z. As we see here, X was 1, Y was 2, and Z was 9. So that's the basics. Notice that these 3 ways of defining our variables did the exact same thing, which is good. So that's the first part of it, which is the most basic input-output things. Let us now talk about inputs, actually. I did say input-output, so we may as well talk about inputs. There's 2 ways that we can get inputs. One of the ways that we can do it is by actually giving our function an argument. So normally when you do your functions, you do stuff like f of x, and the assumption is that you want to put this screen share is really annoying. Let's see if I can move it out of the way. There we are. And the assumption is that you'd want to like put something in this x, right? Oh, and look at that, they kept the variable x from before. Anyways, so that's what we can do here. Maybe instead I'm going to define test of x, and what we're going to do is that I'm going to it's so because basically I've used x as a variable here. I can't really use this one again, so maybe I'll give it another name. Let's just call it a. Okay. So now this function is actually going to want an input a, and maybe at the end here, all I'm going to do is just print out a plus 1. Okay, quite simple. Let's check the syntax and store, and then let's run again. Okay, so now this test function actually wants an input into it. If I just input nothing, it's gonna give me an error of too few arguments because we literally ask it, oh, we want a value of a. It's looking for a value of a. So let's give it a value of a. Let's give it 5. Now, if we were to run this code, you might guess that we want to print out 6 at the end. So let's see if we do that. We do indeed print out 6. So notice, we first display out x, y, z, which happens here, and then next we print out 6, which is just what occurs in the line next afterwards. Cool. Okay, so that was one way that we could check for inputs. Another way we can do it is actually using something called, if we go for input output again, we have this one called request over here. And as the name suggests, it basically requests the user for an input. So we have to first give it a message we want to give the input so that the user knows what's going on. So let's say give me a number, okay? That could be our request. We're going to request the user for a number. And then after that, we're going to assign whatever the user decides to input into here into a variable. Just like that. Once we've done this, once the user has given a number and we've assigned it to b, we can then use this variable b. So maybe the next thing I want to do is just print out b squared, okay? Remember, b squared is just b squared. Notice how we can like write maths as normal in this program, so that's good. What I might do actually, I might delete some of these stuff here just to simplify our output slightly, because I'm assuming now we know how to define variables. So let's leave it like that. We can get rid of x, y, and z then. And we just have this, okay? So we're going to input in a value of a up here, and it's going to print out a plus 1. And then the function is going to request the user for a value of b, and what should happen is that we print out b squared. So let's see if this works. I'm just going to check the syntax again, because, might make a mistake. Okay, the CAS seems to think it's okay. That's good. Let's see if it works now. So, number 2, and free for run. Let's I want to give a value of a of -1. So we run it, we see it's already printed out a plus 1 down here, which is 0. And now it's asking us to give a number. So I'm going to give the number of maybe 67, okay? Notice this is quite similar to, you would have seen a lot of CAS, if you've done much work with the CAS, you would notice a lot of CAS inbuilt functions have these little pop-up boxes. So yeah, it's very useful stuff. And oh, look at that. So look, we get the message and we get our output as well. Great, tells us a lot of information. That's cool and all. So that is the basics of, input, output, defining variables, which is, the most fundamental part of your code. You notice here though, there's a lot of other stuff that, we haven't talked about yet. Stuff that unfortunately we're not going to cover because we just want to go through the basics, which will be relevant for VCE. But I would encourage you, if you are interested, to just explore around here and see what we can do on this language. Okay, so I want to talk about a quick thing, which is how to define functions within our program. This turns out you do it the same way you'd always normally do it. Okay, so when you're doing your pseudocode, you would probably define functions something like, define f of x, and then return some shenanigans. Okay, that's how you would do it in your pseudocode. It's extremely simple on the CAS actually. So the way you do it on the CAS, actually maybe I should have kept that here. Let's just keep that. The way you do it on the CAS is simply f of x, for example, is equal to x squared. Just like that, and we're done. And then we can proceed then to use it. Literally just like that. This is literally all you do to define a function on the CAS. It's very, very simple. So let's run this code. 25. Nice. Okay, I want to talk about something that's a bit important here, okay? Because it is very important for when you're writing these things. Maybe like in an exam when you're trying to test pseudocode, maybe just as you're preparing for a SAC or a test or any sort of exam, where you want to maybe write some functions that can help you do certain tasks, which is something that I would recommend every student do. Because, you're just using the power of this CAS that's available to you. So when you're writing out these functions, you might do stuff. So I've got an example here. Okay, it's a pretty useless function, but it is a function anyways. It does stuff. It gives me an output. So I've just defined a equals 1, b equals 3, c equals 6, m equals 4 in several different ways, and I'm displaying this. So if I run it, I can go like, oh, it runs. I'm happy. That's cool. I can run it again. It runs. I'm happy. So you might think that's okay. I've ran it. And then further down the track, you might realize that like if I want to then maybe do another question and like I want to maybe write some variables A, I noticed that, hang on a second, my variables are already defined. That's really annoying. A, B, C, and M are already defined. And the reason why is because we define them over here. And the CAS treats CAS math as just math. So it just defines this as it is. But that could be kind of a problem here because, like, um, you know, this is just really messing up all the variables that we have defined. And especially if this was an exam, this might actually overwrite the definitions of some variables you are using in some previous questions that maybe you wanted to check out. So this is kind of problematic. We don't want these variables to be leaking over into our other documents. The reason why they are is because these are what you would call global variables because they apply globally to our entire document. We don't want that. We want these variables just to exist within our program to calculate, just for us to calculate them. That's it. So we have a solution to this, okay? What we can do, and I would recommend doing this for all your functions that you use, is that we're simply going to first declare that these variables here is that we only want them to exist within this little function here or program. So we're going to declare them as local variables. So we can use the keyword local. You can find this in define variables 1 for local as well. And we're just simply going to say that A is a local variable to start off with, okay? We're going to say that B is a local variable. We're going to say that C is a local variable, and we want M to be a local variable as well. Like that, A, B, C, and M, we've now said are local variables. When the CAS sees this, it's going to go, oh, okay. So we're just going to have these variables A, B, C, M over here just for this little scenario. And then once it's done, we're going to clear it. We're not going to override existing variables. We're just going to, these are just 4 happy variables existing in their short-lived lifespan within this piece of code. So let's refresh everything. So to do that, I'm going to go to clear A to Z to clear all my 1-character variables. ABC, freshly undefined. Great. Let's try run this one again and see what happens, okay? We've got 14 again, but now notice A, B, C, and M are no longer defined on our other document. So they haven't leaked over. So that's really good. That is exactly what we want, okay? We want this to not interfere with any of our maths, which is, what I've done. So for the rest of these examples, I'm not going to bother putting these local declarations in here, but when you're running your programs in your tests or whatever, or just in any situation, you should always do this, okay? You want to avoid accidentally messing up your maths, so you should always define your variables as local variables. Okay, that's all. We're going to move on to some other interesting stuff now. Okay, so I've got a document over here, and we've got some written instructions here, which basically runs through what I've just explained. So I'm gonna scroll slowly so that you guys have the opportunity to pause and read through this if you want. Yada yada yada. Yep yep yep. Should be okay. Should be okay. Okay. I've got an example question that we can maybe use to demonstrate how if statements work. We're going to keep this code as simple as possible, but I'm going to make it a bit obscure just so we can demonstrate how to write some if statements. So I've got a maximum of 2 given numbers here. This is quite simple to do, using just some if blocks, right? Let's write some pseudocode for it. So maybe I want to input 2 numbers A and B for this, okay? Mind my bad handwriting. I'm trying my best. But my handwriting is pretty abominable, so bear with me. Okay, we're inputting in 2 numbers A and B. Here's a simple thing, right? If maybe A was greater than B, then we know A has to be the maximum, right? So we can write, so maybe we can display out. Oh, I'm already using the CAS language, so print, same thing, right? We're displaying. Come on, arrays. Okay, we're going to display A. Else, if if this is not true, the next condition will check maybe if B is greater than A. And then we're going to display B, because then B would be the bigger one. And a rookie mistake would be forgetting the case when A was equal to B. If A was equal to B, then we would check this, that would be false. We would then check this, that would be false as well. So I'm going to add a final else statement here and simply display, well, if A is equal to B, the maximum is going to be either A or B. So it doesn't matter, I'm just going to display A. Okay, now I know that this piece of code right here is definitely not the most efficient way to write in a maximum. However, the reason why I'm doing this is to simply demonstrate how the if statements are written on the CAS. Once you know how to write this, you can do pretty much anything you want. So let's write this down. Let's convert this into CAS language and see how it's done. So over here, I've got a blank slate again. We could type out the stuff manually, or we can be lazy and use some of the great features that this CAS has provided for us, such as number 4 for control. Look at that. We've got ifs, then end this, we've got if then else end ifs, we've got else ifs, and we've got some other great stuff. Ooh, look at all that stuff. So I think, so they've got like these nice templates here for us to use. I'm going to bring in number 3. Look at that. We've got a great template and we can see how it works. The first if statement here, we need like a then afterwards. This is just how this language operates. So the first thing is that if A is greater than B. Ooh, I should maybe also remember that in this case, if we're trying to find the maximum of two numbers, we want two numbers, A and B, right? Can I change the name? Here's the one thing about it. You can't really change the name of your program afterwards. So I'm going to keep it as text. But note, and maybe I'll just write this in using quotation marks down here. We are trying to find the maximum. I can't spell. Okay. So the first conditional check is simply that A is greater than B. If this is true, then what do we want to do? Well, we want to display A, because A is the bigger number. Okay? In the middle here, I'm going to now add a else if block. So we could type else if, right, on the keyboard, or we've got over here else if then. So notice the else if also needs a then in front of it. Okay. Now the next part of our pseudocode was typing else if B greater than A. So let's, do I have any sus tabs open? Hope not. Okay. Else if B is greater than A, then, ooh, that's interesting. So, make sure you have your indents. It's good coding practice. I'm not sure if the language actually requires them, but it's good to have. You can just do an indent by pressing enter after your keyword. Okay. Else if we're going to display B. And then finally, else, if none of these are true and A is equal to B, then we're going to display A. Just like that. And that should be the end of our program. So let's, you know, the usual stuff. We're going to check syntax and store, and then we're going to run. Let's give two numbers. Let's try 5 and 7. What's the max of that? Definitely 7. That's good. What about maybe 5, maybe negative 15 and negative 64? Well, it's negative 15. Okay. If I were to run two numbers identical and we get an output. Great. Looks like it works. Something else I almost forgot to point out was, you know that CAS actually already has a max function inbuilt. So like this whole thing was entirely a pointless demonstration of code. Like, make sure you guys are using this in your questions. It's potentially applicable in some situations. So keep that in mind. You know, this is an inbuilt function. Use it. Okay, I've got a second example here, assigning a letter grade based on a mark out of 100. Let's do that. I haven't actually given us the thresholds for marks, so I might just quickly make that up. Let's go back to our program here. Let's delete all this. And let me just make up some thresholds, shall we? Let's go maybe, what should I say? Let's say A is 90 plus, right? Fair enough. We can maybe say that B is 80 plus. We just make it very basic here. C is 70 plus. This seems reasonable, right? Can I do this? Nope, doesn't seem like it can. Oh well. D is maybe 60 plus. Okay, we're going to say E is 50 plus. And then anything else is a fail. Or an F. Okay, we're going to be nice and say F, not fail. Don't know if that makes it any better. Okay, simple grade system. Now your job is to write up some pseudocode for this. Okay, maybe we're gonna wanna maybe let's we want to give an input as a grade. So remember, there was two ways to do an input, and we want to output the grade we got. Okay, so input in a score out of 100, output our grade. So maybe give yourself some time to do this question and pause the video, and I'm gonna explain the answer. Okay. Okay, hopefully you guys had some time to try this out. Okay, I'm gonna reveal my answer now, and your answer should be something similar to this. I'm not really Ooh, that was the answer there. Okay, well I'm gonna reveal it anyways. May as well. Here you go, guys. So the way I've done it is I've used the request to give an input. You could pass it into this function as an argument. That's okay as well. Either way, you should have some variable called grade, which is your mark out of 100. Now, something that is pretty good coding practice is to actually first verify whether your grade is valid. Obviously, you want a grade between 0 and 100, so anything outside that range we should probably reject. So this is what I've actually done first. The first message I've caught here is simply to say, if our grade is less than 0 or it's greater than 100, then that's not a valid grade, so let's just get rid of it, okay? Whoops. So we're going to actually just display now. We're not getting a grade, it's just invalid. Something interesting, I use this little keyword OR here, which is a valid keyword on the CAS. The CAS does understand what AND and OR is. You might have seen this when you're doing some solves in the solutions. The CAS says AND something or something. That is something that you can do. It's very useful. So if you're trying to, for example, define some conditions when you're solving things, or maybe in general, you just want the idea of AND something, two conditions happening at once or something, you can use these keywords and OR as I have done over here. Okay. Now, once we've filtered out any invalid grade, then we can start checking. So, if our grade is greater than 90, then we want to give it an A, right? So then we give ourselves an A. Or, if our grade is greater than 80, we want to give ourselves a B. Or if it's greater than 70, give ourselves a C. I think you can see where this is going, right? If it's greater than 60, D, greater than 50, E. And then after that, you failed. So, you're a disappointment. Let me just quickly check this. Please work. Oh, it does work. That's good. Okay, let's run this out and see if it works. So, my function had no arguments, so I'm not going to put any arguments there. We're just going to leave it as it is. Give me a mark out of 100. Let's see what happens if I type something greater than 100. Oops. That's not good. I think we need a mark that's actually within 100. Maybe let's go 95. Sorry, 99. Okay, because I'm really good. I got an A. That's nice. What happens if I maybe... Stupid slash. What if I get a bit of a worse score? Ugh. I got a D. That's a bit harsh. Yep. And if I get a really low score, it's unfortunate. But we know our code works, which is very nice. Okay. Let me teach how for loops work. These are quite interesting. So when you're doing pseudocode, at least for a VC standard dose code, you would probably write a for loop something like this, maybe for I from A to B or something like that. And I would just go one by one from A to B. That's cool. That's a for loop. Here's how to do it using CAS. Let's go for control, and we see over here the CAS has already given us the syntax for for. Notice we have to end our for loop. We've got these two commas here. What does that mean? Well, let me note this down. What these two commas means, it's actually giving us an opportunity for three arguments or things to put. The first thing we want to put is your variable. Okay, so normally I think this would be an I, right? The second thing you want to put then is the start value, and at the very last thing you want to put the end value. So what do we have here? We go start to end. So if we want to say from I from A to B, or let me give some values for A and B. Let's say 1 to 5 maybe. Okay, pretty standard values. We can go for I from 1 to 5. And we give I from 1 to 5. So now if I were to display I, let's do I squared for I from 1 to 5. Let's see what happens. So let's run it. Oh, look at that. We've got the square numbers from 1 to 5. So that works. Another interesting you can do, I'm going to change this up a bit. Let's say maybe I want to go just even numbers up to 10. But I only want even numbers. How can we make it only even numbers? Well, we can actually, this is something secret, but you can actually add a third comma. And then afterward, you can put how much you want to increment by. Okay, this is your increment. So like this, what's going to happen is you're going to start from 2 to 10, but instead of incrementing up by 1, we're going to be incrementing up by 2. So we're going to go 2, 4, 6, 8, 10, like that. So let's see what happens now if we print out I squared. Look at that, we've just got the even numbers squared. Hopefully you can recognize square numbers. Yeah. So that's a little secret thing that you know might be useful. But this is the main thing, you know, this increment over here is optional. If you don't include it, it still works fine. It will just increment by 1. Okay. Equipped with your knowledge of for loops, let's try to do an example here. Quite simple, okay? We're simply gonna calculate the sum of the first 10 square numbers. Yeah, sounds basic enough. Let's do it. Okay, hopefully you've had some time to do it. Okay, sum of the squares of the first 10 numbers. Let's quickly do it. I'm gonna actually do it on a blank slate because this should be pretty quick to do. We want a for loop, obviously, and I think your pseudocode. Let me make up a new text file. Okay, Notepad didn't open. I'm just gonna write our pseudocode up here. Yeah, pseudocode. What should you do? I think the general way to do this is you probably want to start by having some variable represent your sum, and we start off at 0, you know, because 0 is the additive identity, right? Yeah, s is 0, and basically you want to iterate from 1 to 10, and for every iteration of that, right, you simply want to add your I squared to that. So you want to add basically the square of I, which goes from 1 to 10, to your sum, and in the total, you should get the sum of the squares of the first 10 natural numbers. Let's now implement this on the CAS, okay? So we have here clearly for I from 1 to 10. So we want a variable I which goes from 1 to 10. And what do we want to do? We want to basically add I squared. Now, don't forget, I actually need to define that our sum is initially 0 to start off with. Once we've got this, all we have to do is simply print out or we display our sum. And hopefully what you get is the sum of all the numbers from 1 to 10. Silly mistake. Silly me. S equals 0 doesn't define a variable. I wish it did. But this language is a bit special, you know? You can't just say s equals 0 and define s to be variable 0. So what I've ended up doing is just displaying out the letter s. We have to actually define s equals 0. Now we actually set the variable s to be 0. Oops, my bad. But, you know, shows a process of writing code. You know, fix these small syntax errors till you get it right. Oh, why is it displaying 0 now? Simple. Over here, I forgot to do it as well, hey? When you do s equals s plus I squared, you know, you should also make sure you actually define your variable to be that. Otherwise, the CAS is just going to read that and go, okay, but I'm not changing s. You haven't told me to change s. We have to actually say to change s. So you can do that. I might do it a different way just to emphasize the fact that there's more than one way to do it. I wish I remembered this earlier. Now let's do it properly. Okay. So that was a bit of a painful thing, but we have finally gotten our answer after that arduous process. So it's good. We got our answer. We're happy. We're happy. I do want to point out, actually, here's another cool way to do it. So this is something they won't teach you, but the CAS actually has a sequence function, which will generate a sequence. So if I wanted, I could... I need to actually delete my variable I first. Okay, so I can actually generate a sequence of I squared for I from 1 to 10. And it's going to give me a set of the sum of squares. So if I then sum it up, I can also calculate it that way. That's something they're probably not going to teach you, but that's pretty cool. You can do that as well. Let's talk about while loops, okay? So, I mean, while loops, we know they have to... You're going to keep on looping infinitely until our condition breaks. Or so we're only going to actually enter the loop and continue looping if our condition remains true. So let's figure out how to do this. We have a 6 here. While loops are fairly simple, right? It's just while the condition is true or false, right? Then we can simply execute some code. So let's write up some sample code that we can maybe use. Maybe I want to have a variable s. Now let's use like x. All right, x is going to be 5. And maybe I want to say while x is less than 10, we're going to run some code in the middle. Who knows? Maybe we want to increase x by 1.5. Okay, and then we're going to display x squared. Pretty random code. So x plus 1.5, sorry. We want to increase x plus 1.5. And then we're going to display out x squared. If we run this code, what should happen is that x should start at 5. We should loop through this again until x is greater than or equal to 10, or in other words, until this condition is not satisfied, and then we should exit. So maybe at the end I'll say exited successfully. Okay, let's run this, and look at that. We've got, a bunch of square numbers. I expect fractions because I was doing like plus 1.5, and we finish and we exit. So that's good. Okay, and if you wanted to like check each output slowly to make sure that this while loop works, you could do that as well. I also want to maybe like write this using decimals, so let's do that as well. Great. So that's a while loop. Using that, let's do an interesting question now. Okay, I want to divide 72 by 14 and simply return our quotient and remainder. Have a go at doing this and come back with a solution that hopefully works. Okay, I'm back. Hopefully you guys have had some time to do it. Your code should look something like what I've got over here now. Okay, I start by just defining a remainder of 72, and my general strategy with this is to do division by repeated subtraction. So we're going to keep subtracting off copies of 14 and increasing our quotient by 1 every time we subtract off a copy of 14 until we reach 0. Simple. Notice though that there's something interesting about the way I've done it here. I've put that we do it while our remainder is greater than 14. This is an interesting one. You might want to think about why it is that we want to do that. Why do we want to do that our remainder is greater than or equal to 14? Because some of you might have thought we can just do remainders greater than or equal to 0. And I guess it really comes to the last iteration of this for loop. Let's think about what happens at the very last. Maybe our remainder, I don't know what our remainder is. Let's say at one point, our remainder is like 15. What happens? We enter this while loop and we see 15 is greater than a 14. So we're going to keep going. We're going to subtract our remainder by 14. So now it's going to become 1. Our quotient is going to increase. And at this point over here, we should end up with our final answer. So now our quotient increases to our final answer. Because at this point, we can't subtract any more from our remainder. So this remainder becomes our final remainder. And the quotient that we calculate here should be our final quotient. If our condition was greater than or 14, this works fine. But then what happens if instead this condition was greater than or equal to 0? Well, what we're going to do, we're going to reach the end of the loop. We're going to go back and we're going to check again if our remainder is greater than or equal to 0. And you'll see the CAS sees that the remainder is equal to 1, so it does satisfy this condition. So we're going to end up subtracting another 14. When you can't subtract 14 from this, it's done. Stop, bro. Stop. It's still going. So we're going to actually do this loop one too many times. And I'm going to demonstrate this right now. So let's do this. Okay, I don't need these brackets here. Let's run it. Okay. We see we've got 5 and 2. So when 72 divided by 14, we have a quotient of 5 and a remainder of 2. Let's check this, okay? So I can do a mod to get the remainder. If you guys didn't know, now you know. So the remainder is 2 indeed. So this mod will take actually the remainder of 2 numbers. And to get the quotient, let's just do 72 over 14, okay? We get around about 5. So that verifies, yes, our quotient is going to be 5 plus some remainder. I love this 142857 thing. It's so beautiful. Okay. Let's adjust this slightly so that we did greater than or equal to 0. And we'll see what happens, okay? Now if I were to run it... Oh, what the heck is that? We've got a remainder of minus 12 and a quotient of 6. That's not right. I mean, yeah, no, that's bogus. That's nonsense. Of course it's not right. So, yeah, unfortunately not. well, mathematically, this is still technically correct. It's not correct. So we have to keep it as 14, which is just a small technicality, but that's something you have to be careful about when you're writing your code. You should always check at the start and at the end of the loop to make sure the order of instructions is doing everything you want it to do. Because, the CAS doesn't know what we're trying to do. The CAS is just trying to do it. It doesn't understand this stuff. You have to explain it to it. It's just a computer, flipping electrical signals and stuff. It's not smart. Yeah, let's go back to this question over here now. We've written a pseudocode, we've calculated it. The third question is interesting. How can you change a code that you can enter any number in divisor and receive the corresponding remainder in divisor as outputs? I think they're meant to say quotient and remainder, so let me change that to quotient. I'm writing with my mouse, which is extremely difficult. Okay, quotient. That says quotient. Okay, and we're also going to probably assume that our two numbers and divisors here are just natural numbers, just to make things a bit easier for us, okay? We haven't really talked about like quotients and remainders when dividing by negative numbers, so let's just leave it as natural numbers, okay? Let's see how we can maybe modify this code slightly. Try yourself. So ideally what we want is up here, we want to basically input in a number and divisor. And we should modify this code so that it works to give us a quotient and remainder for regardless of whatever input we do. So try it out. I've got a bit of a skeleton here so that you can edit if you want. And yeah, come back once you're ready. I hope you're ready. Let's go through this, okay? So our number here is basically the number we're dividing by. So we want our remainder to basically start with this number. Quite simple. Once again, our quotient is going to start from 0. And we're also going to do the same while loop of repeated subtraction. This time we're going to subtract by our divisor step by step. So in this while condition, instead of remainder greater than 14, we just have to change it to remainder is greater than our divisor. And honestly, I think this is it. Once we run this code, okay, we should be able to just get a quotient and remainder. So let's check it, okay? Let's see, what happens if 4 is divided by 1? We should get a quotient of 4 and a remainder of 0. Very nice. What happens if maybe 16 was divided by 5? We should get a quotient of 3 and a remainder of 1. See, we do. Great. Okay, and look, there's no reason why you can't format this a bit better as well. We can write quotient is, and then our quotient, and then we can say in a new line, remainder is, comma, remainder. We can have nice looking functions as well. 74 divided by 15. What's the quotient remainder? I think it's 14. It is 14. Look at that. And we get some nice text here to actually help us understand what's going on. So this is good. This is working. Okay, now example 5 is an interesting one. So we're going to approximate the square root of 11 because for some reason maybe our CAS has just broken. We've forgotten how to calculate, the square root button doesn't work. We need to approximate the square root of 11. We've got a great little program to help us approximate it. Okay, the pseudocode is written here for you. We can have a little analysis of what's going on, but the rough idea is we want to keep applying this like approximation algorithm here. We just like iterate through it again and again, so that eventually we end up with something that's close enough to 11. Look at essentially what's happening here is that this 10 to the minus 4 is essentially our precision. We want, like, as long as our actual result is bigger than this number, which is just a bit over 11, and it's smaller than this number, which is just a bit less than 11, then we want to make it we want to make it more and more precise. So overall, our number should fall within a range of 10 to the minus 4 within 11 once we square it. So that's our goal. Actually, let's do this one together since, it's pretty chill. Okay, let's delete all this. Oh, I feel bad deleting all this great code. Nah, it's not that good. Okay, just to find our test again. The first thing is that we want to set A to 3, so I can do that. I'm actually going to do it using the arrow this time because, arrow. So we want to put in a while loop over here. And the condition is this. A squared is either greater than 11 plus 10 to the power of minus 4. Notice we've used the or again, this or keyword. We can do that. Or we want A squared to be less than 11 minus 10 to the minus 4. Then we say it's not precise enough, and we want to apply this algorithm over here. So let's do it. We want to set A to become 0.5 times, okay, bracket, a plus 11 over a. So a plus 11 over a. Then we want to print a and a squared, so we want to essentially display a and a squared. And that's the end of our while loop. So I have a feeling this might be quite satisfying. So let's see how this goes. Let's check the syntax. And let me just quickly double check this myself to make sure this looks good. Yeah, it looks good enough. It should run. Let's try it out now. So, oh, it's kind of ugly. Let's maybe use some decimals, shall we? Wow, look at that. So we run through it a bunch of times. We see our first estimate is that, which is close but not too close. We have another estimate, which is that. It gets a bit better. And then our third estimate, the CAS is like, yeah, that's precise enough. Let's leave it at that. And that's very good. So we get a really nice approximation for, well, the square root of 11. It's roughly equal to 3.317. Who knew? Now you do. Okay, so answers are out 3.317. Let's do that. Okay. Nice. I've got two more examples here. I'll go through 2 more examples with you guys, okay? The first thing we're going to do is calculate the first 20 terms of this harmonic P series over here. Which, I mean, just that. The first 20 terms of that, okay? Yeah, what can I say? Use a for loop and go calculate it, okay? Do that, and I will reveal the answer. Okay, let's see what I've done here. So I've got the test, okay, and you've done all this stuff. So what I've done, I've started by having a sum be 0, okay, and we're saying for I from 1 to 20, we're simply going to add on to our sum 1 on I cubed. So this is going to add on 1 on 1 cube, 2 cubes, so on, all the way to 20 cubed. Okay, and at the end here, I just want to display out our S. Fair enough, let's run it. We get that horrific answer, which is about equal to that. I'm going to check it by once again doing simply the same thing. We're going to do the sequence of our i's, sorry, of our 1 over I cubed for I from 1 to 20. Okay, ignore the fact that I is defined. It actually doesn't change it here. It's going to treat I as its own variable. And we get the same answer. So, yeah, we've checked it 2 ways. That's good. Okay, you can always simply, I mean, you should know if you watch the video how to get rid of I being accidentally defined. So, yeah, we've got that very nicely done. So we can write our final answer here to be around about 1.2. Okay, last question now. We're going to need to talk about the bisection algorithm, which is about solving this equation over here using the bisection algorithm. You'll have to look on your notes maybe if you forgot how to do the bisection algorithm, but as a rough idea of what we're trying to do here, we're essentially saying that we're taking an interval and we're going to evaluate f at each of these intervals here. And we're basically going to see like where the sign changes. Okay, we're going to evaluate f at these intervals, and then we're also going to evaluate f at the middle here. So the middle would be a plus b on 2. I'm just roughly outlining the bisection algorithm, but this is something you should definitely study if you're not familiar with it. Because what's happening is we're going to look at where the sign of the graph, essentially where it's going to go from positive to negative. If your function goes from positive to negative over here, then we know that the x-intercept has to lie between a and a plus b on 2. So then we basically set that to be our new interval and we repeat this process. If we know that the function goes from negative to positive or positive to negative in this region between a and b, then we know that our x-intercept has to lie between either the middle or b. So we set our new interval to be there. And we're going to repeat that process until we can get it to an accuracy of 2 decimal places. So yeah, you've got a lot to think about here. Like, how do I ensure it's going to be accurate within 2 decimal places? Yeah, and like you might also want to think about how exactly we can maybe write a function for it. Maybe that's a hint. Have a go at this. Okay, this one was a bit more of a challenge, but hopefully, if you wrote out a solid process, maybe you started with some pseudocode and just wrote some good code, you could have got it done. Let's start with our first part, which is just setting things up. we want f of x to be equal to our expression here. Hopefully I wrote f of x correctly. It is x squared plus 3x minus 6, which is good. We want a, so a and b is basically going to be the start of our interval. So our initial guess. When I see a cubic, I see that it only does... When I see this type of cubic, I do notice straight away that it only does have one solution. So we can be quite generous with our interval. I'm going to start from -5 to 5, and honestly, you can just like check. You can probably just check first, just to make sure your interval contains it. But yeah. And our m is just simply going to be the middle to start off with, okay? We'll just start off with that for now. Now we're going to go into the algorithm. What I've got here in this while condition is basically a tolerance. We're going to say that if, when we're calculating f of m, if its absolute value is greater than 10 to the minus 4, then that means with it's not, if like essentially like, yeah, the absolute value of f to the m is more than 10 to the minus 4, then we say it's not accurate enough and we want to keep repeating this process. Okay. Notice that all this absolute value means that, if, for example, it was our f of m was like -1, the absolute value of that would simply make it 1. Okay, and then in this case, yeah. So essentially what this is giving us over here is simply how far away it is from 0. So if it's more than this much away from 0, then we say that our value of m isn't good enough. My decision for 10 to the minus 4 was the fact that we needed 2 decimal places of precision, right? Or in other words, we needed precision up to the nearest 0.01, which is 10 to the minus 2. Something that is like a general rule of thumb is that accuracy will, that the decimal point accuracy will be the same when we like apply functions to it. So given that, I assumed, 10 to the minus 2, that's sure, but let's just be extra safe, and I just bumped it up to 10 to the minus 4. So now it's accurate to the nearest thousandth, which just, nearest 10,000th, which just makes it extra accurate, which is good. And let's run through this code now. What I've done here is saying, okay, so if the function were to go from positive to negative between a and the middle, right? Then if we multiply them together, one of the either f of a or f of m, one of them should be positive, one of them should be negative. So when you multiply them, they should be less than 0. So if that's the case, well, we're going to shorten our interval down. When it was initially a to b, now it's simply going to go from a to the midpoint. So in other words, our new value of b, or the right-hand side of our interval, should now be the midpoint. And then our midpoint should now be, yeah, sorry, I had a moment. And then with this one, okay, if the place where the function changes signs is between the midpoint and b now, well then essentially this midpoint here wants to be our new a. We want to keep b where it is, and then we want a new midpoint, which is just a plus b on 2. So that's what I've done over here. Okay. Now, you just want to be very, very careful with this, is that you want to be careful that the order in which you define variables is correct. If I had moved this m upwards like here, maybe, in front of that would have actually created a mistake, because you have to think about what the variables are at every single stage, okay? If we change the value of m over here, and then proceed to define a as m, which we've already changed down here, this is not going to work, is it? Think about it, right? We're going to end up, because if this is defined first, and then a is then defined as m, we're defining a as this, which means that doesn't work. So you have to make sure we define a first before we change our value of m, okay? So once I've done that, okay, once, f of m does fall within this precision of 10 to the minus 4, the condition breaks, and then we end up displaying our value of m. Let's test this. Okay, and we get this number over here, and if I approximate, that's about minus 1.28. Okay, let's use the same f of x that we have here. Oop, let me delete x. This is why I should use local variables, okay? Same f of x over here. Let's actually calculate what the actual x-intercept is now. About minus 1.288, we've got about 1.288. So we got it very accurate. So our code does work indeed. So our final answer is just going to be minus 1.2, what is it? 1.29 if we're going to round it to 2 decimal places. Okay, so yeah, that was a good basic summary of pseudocode. Hopefully you are a bit more confident with, hopefully you know how to use one of these things now. Very, very cool stuff. Lots of stuff you can do with it. I would encourage you to go play around with this. Just like, there's a lot of stuff I haven't covered, and it's all in the menu. Go have a look. You can even go read the documentation, see what is possible. There's a lot you can do with this. Okay, so go have fun and explore the possibilities. But this is going to be the end of this lesson right now. Yeah. Okay. Go. Make sure you go study.